Thank you so much. Okay, let's share my presentation. Can you see my presentation?
Yes, sir.
Okay, thank you so much. So, good afternoon, everyone. Today we will discuss about some, let's say, case studies, and mainly the implementation of mitigation technologies in large scale and real scale, really, cities. I decided not to go through too many, let's say, implementations and too many case studies because I wanted not to be superficial, and I wanted really details and present you really what can be done in a very specific project of implementation in order to understand the details. Because okay, it's nice to present the let's say the type of materials used or whatever, but I think that always the devil is hidden behind the details. Counts is more the methodology of the mitigation studies and the methodology of the implementation. So I will present you today one of the very, let's say, recent studies that we have undertaken here in UNSW in Australia, together with, let's say, other colleagues from, let's say, the Lawrence Berkeley Laboratory, and also the National and Kapodistrian University of Athens, and the National, let's say, the company National Drones, and the University of Calcutta in India. And this is a project in Riyadh of Saudi Arabia. Riyadh in Saudi Arabia is really a very warm city. Temperature during the summer period is about, and the Saudis have decided really to improve the environmental quality of their city. So they have started a very extended heat mitigation project in the country, and in order first to decrease temperature and improve the, let's say, overall city. Riyadh presents really an important urban heat island. You can see from the graph in the upper part that the center of the city is really 3 to 4 degrees higher than, let's say, the surrounding areas. Riyadh is surrounded by desert, and this is extremely important because this defines the boundary condition for the whole, let's say, implementation. Objectives of a mitigation project. First, in order really to implement mitigation, let's say, mitigation strategies in a city, we have to know the exact problem. If we don't know the characteristics of the problem, we risk really to solve the wrong problem or another problem. So the very first task of this study was to assess the magnitude of the urban overheating in the city, the magnitude of the urban heat island, and the intensity of heat waves in the city, of course, based on existing data. Also, to understand really the spatial distribution of the overheating in the city and assess the hotspots and classify the severity of urban overheating in the various parts of the city, to understand the thermal comfort and the thermal heat risk really in the city. To perform at the same time a land use and a land cover analysis for Riyadh, to understand really all the details about really the land cover. Why? Because this defines really the characteristics of the thermal performance of the city. And collected, we had to identify the main causes of the urban overheating in the city. This is the most important part of a study. Without really understanding the real, let's say, reasons behind the overheating in the city, we cannot really design any methodology, any heat, let's say, mitigation strategy or design any, let's say, strategy that will improve the climate in the city. Once really we understand what's happening in the city, the most important is really to define the most appropriate heat mitigation technologies for the whole city using, let's say, advanced technologies. And these advanced technologies have to do with the use of materials, greenery, and different other combinations. It's really the type and the characteristics of the heat mitigation strategies are really selected. It is very important to assess the cooling potential and the distribution of the main climatic parameters in the city when this. So, based on it, we have to prepare, let's say, maps with the main climatic parameters in the city. Yeah, for each, let's say, mitigation scenario, trying really to understand and at the same time communicate the problem in the city. At the same time, to prepare a full climatic mapping of the cooling potential in the city and prioritize strategy scientists, but for the decision managers to, let's say, give them in a very clear and comprehensive way to understand the reasons of the problem and present them the solutions in a simple way. Otherwise, they are lost, and otherwise, they select always and they choose simplistic solutions that unfortunately they don't have the proper, let's say, result. And of course, once really the mitigation technologies are selected and evaluated, we have to assess the impact of each of the mitigation technologies on the energy consumption. What really happens when these mitigation technologies are implemented to the city? How really we can decrease the energy consumption? And how really this will help to mitigate heat and how really this will combine in order to adapt the city to new climatic conditions. These 10 major objectives were really the main aims of the specific study. Then, once the objectives are well defined, it is very important to define the roadmap of the study. What do we have to do? So, our study had a very clear roadmap combining that really started from the analysis of the existing climate. We have collected all the existing climatic data from all the meteorological stations that analyze all this data to understand really what is really happened there and to, let's say, evaluate the characteristics of the climate during the whole year, the temporal and the spatial variation. In order to be prepared for, let's say, the evaluation of the existing situation and also of the future conditions using, let's say, heat mitigation technologies, we have to use some simulation. Let's say one of the best simulation techniques to evaluate the impact of heat mitigation technologies and understand at the same time what's happening in the city is the use of mesoscale climatic models. So we have implemented mesoscale simulations in order to evaluate the climatic conditions during the summer and the winter period. And we have designed WRF, a mesoscale model for the whole city. Then we have collected very important information regarding the specific indicators that define the life in the city. These indicators have to do with the landscape, the physical characteristics, the climatic characteristics, the social and demographic indicators, and everything really that defines the, let's say, links between climate, overheating, and the city and the life of the city. In the fourth, let's say, step, we have perform a climatic and a statistical analysis of the magnitude and the characteristics of the urban overheating, let's say, in the city. Because it was very important, really, to calibrate the models we have, the models that we have developed in step 2, based on the existing climatic data, ensure that the results that we have predicted or we will predict will be accurate, and this can be done only by, let's say, validating the data for the current situation, for the existing situation. So we have validated our models based on the, let's say, collected data. Then we have designed the mitigation technologies, and we have really analyzed the main characteristics of the overheating, the sources of the overheating in the city, the reasons behind the overheating, and we understood such an increase of the temperature. And we really tried to fit the mitigation technologies with the specific problems, not a blind implementation of unknown mitigation technologies. For each of the problems identified, we have designed a new mitigation strategy that really we believe from the very beginning that could really help to decrease the magnitude of the overheating. And we used existing mitigation technologies and advanced mitigation technologies, which are based on the use of materials, greenery, evaporation, and combinations of them. And these mitigation scenarios have to do, first of all, with the use of cool and super cool materials. We will discuss about it. And once really the characteristics of the materials were really selected, we perform mesoscale simulations, and we have calculated the mitigation potential of these materials, the spatial distribution of the cooling potential, and the temporal distribution of the, let's say, mitigation potential for the whole year. Once we have finalized the, let's say, analysis of the potential impact of the different type of materials, we move to the next step, which has to do more with the implementation and valuation of mitigation technologies based on assessment, green technologies. So we have designed some, let's say, implementations for the city and some strategies for the city based on green technologies, and we have really performed the mesoscale simulations, and we got the results. Analysis of the results taken from the simulations for the buildings, for the materials and the greenery has shown that perhaps combinations have to be used to combine the two technologies in a proper way in order to help each other and really achieve the best possible and the highest possible mitigation potential. So in the 8th step, we created combinations strategies, and especially combinations, several combinations of materials and cool, super cool materials and greenery. So we had a full, let's say, documentation of the potential of the mitigation technologies that we have really considered and assessed, and this has to do with 8 different scenarios, and we were absolutely sure that this is almost the optimum, let's say, design of mitigation technologies. Then we had to evaluate the impact of these mitigation technologies really in the city. And the very first calculation and assessment had to do with the impact of mitigation technologies on the energy consumption. We calculated the energy conservation potential of the mitigation technologies using, let's say, some advanced simulation, building simulation, let's say, procedures. And once really we had a very good understanding of the potential impact of all the considered, let's say, mitigation technologies on the energy consumption, We analyzed how really these potential energy benefits can be combined with other measures which have to do more with energy conservation and adaptation in order to prepare and propose an holistic and integrated energy conservation framework. And based on this, we have really calculated for each one of the mitigation technologies considered the energy consumption for a very high number of buildings in, let's say, at the city scale. So understanding which is really the potential for energy, let's say, conservation because of the heat mitigation, and also the energy, let's say, the energy conservation because of the energy adaptation by using, let's say, advanced adaptation technologies. And finally, once the full study was almost completed, we had really to prepare and propose recommendation on the optimum design and the implementation of urban mitigation technologies really that are proposed at the city level. I will stress that it is of extreme importance to have a clear roadmap for each mitigation study. We have first to assess the existing conditions. Second, we have to understand the reasons behind the overheating. Then we have to design strategies, mitigation strategies, which fit with, let's say, the sources of the overheating. We have to evaluate the potential of these mitigation technologies at the city scale and also during the different boundary climatic conditions. And we have to identify the best combination in order really to assess, in order to achieve the best possible cooling, let's say, potential for the city. Once we know the cooling potential for the city, then it is very important to understand the impact of, let's say, the different mitigation technologies at the city scale. And the impact has to do with energy and also has to do with, let's say, some other things. It has to do with energy, and this is done. It has to do also with health. But unfortunately, it was not possible to get and have, the health data for the city of Riyadh because of the, let's say, non-proper, let's say, statistical data that were available. There is also a possibility to perform more studies regarding the impact, peak electricity demand, productivity, and many other things. But this is not always possible, especially when really this data is not available. So I like to move to the next, really, to the next slide, and start presenting you the different steps that I have really shown you before. And the very first one was really the analysis of the climatic data. Actually, in, let's say, Riyadh, there are about 16 different meteorological stations at the city, let's say, level. Along, the whole city. And we got the data for, let's say, all these, let's say, meteorological stations for a period of 5 or 6 years. And we calculated really the distribution of the temperature difference and also the overheating at the city scale. And also we consider some reference stations which are located almost, the suburban areas, not influenced so much by the urban conditions. And so we calculated the differences between the urban and the reference, let's say, conditions. This is done for different synoptic conditions. This is done for the whole year. In reality, most of the time, the differences are close to 1.5 to 2 degrees. 1.8 degrees is the average temperature for the 75% of the time. But under specific climatic conditions, these differences, which indicate the overheating of the city, may be as high as 4 degrees. Also, sometimes we found that the surrounding areas are really warmer the city. And this is not really so, let's say, frequent, but it happens. And it's really very important from the scientific point of view to understand why this happens and which are really the drivers behind such, let's say, climatic conditions. So, having a full analysis of the climatic data, we calculated the cooling degree days. Cooling degree days may show the cumulative, really, impact or the cumulative conditions in the city regarding, let's say, the climatic conditions, and especially regarding the impact on the cooling demand of the city. So we have really calculated the cooling degree hours for a base temperature of 24. Perhaps you may consider that is low, but this is the temperature which is used, let's say, in Riyadh, and this is done for 5, let's say, complete years, and this is done for the reference location and also all the stations in the city. For, let's say, one complete year, the urban stations, in average, present 14% higher cooling degree days than the reference station. And this shows really the magnitude, let's say, during the whole year at the city scale. Once we had a very clear, let's say, understanding of the climatic conditions, and of course, this was a little bit more detailed because we had a full mapping of all the neighborhoods of Riyadh during the whole year and during all the synoptic climatic conditions. We concentrated on, let's say, landscape indicators. Riyadh is one of the many cities in the world experiencing high rates of urban expansion. This is something that leads to changes in the flows of materials. So we collected all the landscape indicators in the For the physical component of urban heat risk, an important indicator is the building density per district, which is the high building density, and this is one of the best indicators, which really defines the increased heat risk. Since, buildings absorb a lot of, let's say, solar radiation and reduce the wind speed, and in reality act as heat traps. In Riyadh, the highest building density is in the southern part of the city, and the higher density also happens, in the eastern district. So we had really all the characteristics at the ground level of the city. To do with the social characteristics. We know very well that elderly people tend to be more vulnerable to heat because they do not adjust well to sudden changes in temperature. We discussed it yesterday. In Riyadh, we have higher percentage of both young and older people in the southwest district of the city. In general, the percentages of older people in Riyadh are very low in most districts, a fact that to heat risk. Riyadh is a city which really is habitated by younger people. But it's very important to know where people is living and the local characteristic, because this defines really the vulnerability and the heat risk. So we had all the climatic analysis and we had all the data about the physical landscape and also social characteristics. We had a very good understanding of the actual conditions. Then we had to proceed with, let's say, the possible solutions. But to do that, we need to be sure that all the simulations to be performed have to be accurate. How this can be done? This can be done by using, let's say, simulation techniques which provide information about the spatial and the temporal variation of the main climatic parameters in the city. So we have designed a mesoscale simulation, let's say a mesoscale simulation scenario, which was really not covering the city of Riyadh, but is covering the whole domain, almost half of, let's say, Saudi Arabia. And then we have simulated for a whole year the distribution of the main parameters, main climatic parameters at, the whole city, with a resolution of 200 meters by 250 by 250 meters. And we compare the results against the existing climatic data under the same boundary climatic and other conditions. And you can see the results of this, let's say, comparison. You can understand that the simulations were really accurate and could predict the existing climatic conditions with sufficient accuracy. This is extremely important for such a study. If you don't perform this, let's say, analysis and this kind of, study, you are not sure about the, let's say, the quality of your data and the quality of your predictions. So, we have defined, let's say, the reference conditions. The reference conditions which really refer to the actual conditions. The analysis of the climatic data from, let's say, the 16 stations provide important information, but do not provide the, let's say, a detailed temporal and spatial variation of the main climatic parameters in the city. And also, it is very difficult from 16 stations to have important information about, let's say, the specificities at the ground level. So by using the already, let's say, validated mesoscale model, we calculated the spatial distribution of the temperature during the whole year, and so we had a reference. So we had for every, let's say, grid, 200 meters by 200 meters, for a whole year, the distribution of the main climatic parameters really at this grid and also at the city scale. So you can see, for example, that the distribution at 2 o'clock at night, the reference distribution shows a temperature at the city level which is close to 30 degrees. At about 8 o'clock in the morning, the temperature is increasing and goes up, let's say, to 37, 38 degrees. During, let's say, the afternoon, 2 o'clock in the afternoon, the temperature is increasing close to 43, 45 degrees. And in the afternoon, 8 o'clock, let's say at night, the temperature is always between, let's say, 35 to 40 degrees. So it's an overheated city, but this was very well known. But it is very important to understand really the range of, let's say, variation of the temperature, not in the whole city as an average value, but to know the temperature, the distribution of the temperature really in the city for each one of the grids, because we have to implement mitigation technologies not generally for the city level, but we have to implement mitigation technology for the different parts of the city. Important also to understand the extreme conditions. What I showed you before was really the average. Now, during the hottest day of the year, at, let's say, during the night, temperature really is not really increasing very much. It's increasing by 1 degree. During the morning, temperature really goes up to, let's say, 40 degrees. And during, let's say, the afternoon, during noontime, 2 o'clock, it goes up to 45 degrees. So it is 3 to 4 degrees higher than the average. And in the afternoon, 40 degrees. So during the hottest day of the year, we have extremely high temperatures, which really are completely unpleasant and create many, let's say, energy and health problems. So based on it, we have calculated the urban heat island intensity. What is the urban heat island intensity? Is the difference of, let's say, the different parts of the grid, the different parts of the city against the defined reference station. And we've done this for, let's say, the whole period. And you can see, for example, that during the night, let's say, urban heat island intensity is close really to 3 or 4 degrees. But during, let's say, the day, the urban heat island intensity may go, let's say, up to 4 or 5 degrees. So we know really what is happening in, let's say, the urban areas, but also in the reference areas. Why this is important? Because of heat from, let's say, from the surrounding areas, which is mainly the desert, to the city. So we have to know not only what is happening at the city level, but we have to know what is happening at the surrounding, because this defines really the advection of heat, the transfer of heat from the surrounding to the city, or let's say vice versa. And this gives us the magnitude of the urban overheating. The magnitude of urban overheating during a hot summer is considerably higher during the night than the day period. And as I showed you before, the whole middle and southwest regions of the city present an urban heat island intensity of more than 4 degrees during the night, while the intensity started to shift to the southern parts from, let's say, midnight. The intensity remains close to 2 degrees most of the day. During the hottest day of the year, the intensity of the urban heat island is 7 to 8 degrees. Why we have higher, let's say, temperatures, higher, not temperatures, but higher distribution or differences during the night? This has to do with, let's say, the complete and the global, let's say, radiative cooling in the city. In some areas, radiative cooling is much, much higher. In some others are much lower. So this really defines how much of radiation it is really released or emitted, by, let's say, buildings and the ground. And this defines also the radiative losses. So the radiative losses define the temperature difference. And the radiative losses really are those that define really the temperature distribution in the city. At the same time, it shows how much convective losses really affect the temperature of the city. But in Riyadh, most, of the, let's say, heat losses have to do, or heat gains, have to do because really of the radiative, let's say, procedures, and less because of the convective procedures. But also convective procedures, and especially advection of heat from the desert, is really, at specific periods of the time, very important. So once really we know the dynamics of, let's say, the climatic conditions in the city and at the city level, and which parts of the city are really affected by this, let's say, heat transfer dynamics, we had a very good understanding of really what is the magnitude of the urban overheating and the relation of the urban overheating with all the other climatic conditions. And one of the major parameters which define the convective and advective, let's say, conditions and advective and convective losses in the city is the wind speed and the wind direction. So the average urban heat island intensity, which is close to 1.6 degrees, is really observed when the wind speed is low. And when really the wind speed is, let's say, is increasing, the urban heat island of the medium speed zone, it has an intensity of 1.4. So this means that in the areas of the city where we have low wind speed, we have higher urban heat island, while in the areas that we have a little bit higher wind speed, the urban heat island is a bit higher. What does it mean that? It means that we have advective forces. It means that really the, let's say, wind speed contributes to decrease urban heat island, which means that let's say, urban heat island is very much affected by, let's say, the convective losses together with the radiative losses that I mentioned before. But in a city, we don't have only to, let's say, calculate and assess what is happening during, let's say, the summer period. It is very important to understand what is happening also during the whole year, and mainly during the winter period. Winter in Riyadh means really temperatures close to 25, 30 degrees. So it's not a very strong winter like we know in Australia or maybe in some parts of India. Regarding the magnitude and the characteristics of the urban heat island during the winter period, we understood that, the maximum and the highest urban heat island intensity happens at about 4 o'clock in the afternoon, and the maximum value was very high, 11.2 degrees. But this is just the maximum. The average urban heat island intensity during the winter period is close between 2 to 3 degrees, which means that the urban heat island is also present during the winter time, and the reasons behind really the differences at the temperature, of the temperature at the city scale are very similar to what has happened during the summer. So the differences and, between the different parts of the city and the difference of the urban heat island intensity have to do with the urban density and the radiative forces. And these differences persist during the day and the night period. Once we had a good understanding of the distribution and the characteristics of the ambient temperature, then we had to, let's say, assess and understand the surface temperature. Why the surface temperature at the city scale is important? Because it defines really the mean radiant temperature, and the mean radiant temperature is very important for comfort reasons, also defines, say, sensible heat, which is released by, let's say, the city's surfaces, and so determines the magnitude of the overheating. So we define really the, let's say, the reference conditions and, of the surface temperature under the average and conditions and the hottest day. And so we have assessed and we have understood that the surface temperature varies between, let's say, 30, 35 degrees to 45 degrees, with sometimes important differences in several parts of the city, and especially in parts with higher, let's say, distribution of buildings. The patterns of the surface temperature follow the patterns of the ambient temperature. And this really helps us to understand the reasons behind really the overheating, which, as mentioned before, have to do mainly with, let's say, the urban density, and also a little bit with the generation of anthropogenic heat at the city scale. In order to be, let's say, well sure and ensured about our analysis regarding the surface temperature, we collected data from satellites and we compare the, let's say, simulation results about the surface temperature at the city scale against, let's say, satellite data. And you can see in this graph the temperature distribution we had for one specific day taken from the satellite. You can see, for example, that the surface temperature difference as really calculated or measured by the satellite are of the order of 5 degrees. The lowest was 51 degrees, the highest is close to 56 degrees. So we compare these, let's say, assessments and these measurements against, the corresponding simulation we have performed and we had, before. And we have, let's say, understood that our simulations regarding the validity of the surface temperature is really quite accurate. Is it enough to know the surface temperature and the ambient temperature? No. One of the major, let's say, climatic parameters that define, let's say, efficiency of heat mitigation technologies, it has to do with wind speed, with the distribution of the wind speed at the city scale. So we have really creating a mapping using simulation techniques, showing really which is the hourly wind speed and in each of the grids. We see that, in high density urban areas, for almost 50% of the time, the average hourly wind speed is close to 4 meters per second, while, in the medium and low density urban areas, for most of the time, almost 99%, is also, 4 meters per second. But you can see, for example, that in, let's say, noontime, in specific areas of the city, the wind speed really is higher than in the other parts of the city. This is very important because this really demonstrates in which part of the city convective losses are most important and more important. And this also, let's say, helps to understand which kind of mitigation technologies have to be used. And in these areas, mitigation technologies which really addresses and fix the problem of, let's say, high convective gains have to be used. And also, we had really to understand which is the zone with, let's say, the high wind speed, the low wind speed, and let's say the medium wind speed. You can see that really most of the city presents really medium wind speed and low wind speed. So convective losses, as mentioned, let's say before, are really important. Advective, let's say, gains and losses are really important, but as mentioned before, radiative, let's say, heat exchanges are the dominant exchanges which really define the thermal budget at the city level. And once we know the three major climatic parameters, surface, temperature, ambient temperature, wind speed, and direction, then we can easily calculate the sensible heat. The sensible heat is the heat which is released by, let's say, the city surfaces, and this is the major, let's say, parameter that increases the temperature in the city. So we have calculated for, let's say, the whole year, the spatial and temporal variation of the sensible heat at the city scale. And you can see, for example, that, let's say, at about 2 o'clock in the afternoon, we have a sensible heat which is close to 150 watts per square meter. While in the afternoon, this decreases and goes down, let's say, to 50, or even during the night, it's a little bit lower. During the day, the sensible heat which is released, the 150 watts per square meter, is very important, which shows us why, let's say, overheating happens and what kind of mitigation technologies have to be used in order really to cool down Riyadh. And the mitigation technologies that have to be done have to reduce the sensible heat at the city scale. But how to reduce the sensible heat at the city scale? Why we have a high, let's say, sensible heat release? Because the temperature of the surfaces is quite high. The sensible heat is a function first of the temperature difference between the surfaces and the air, and also of the wind speed, at the specific area. So in order really to decrease the, let's say, magnitude of the sensible heat, we need to use technologies which really will decrease the temperature of the, let's say, the surfaces at the city scale. And we will discuss how this can be done. But sensible heat is the major heat gain for the city. But also, we have losses. And losses are coming from, let's say, greenery, water, and other, evaporative surfaces. And these surfaces really release latent heat. And latent heat is decreasing the temperature at the city scale. So we have to know the balance. We have to know how much of heat is coming from where and how. And we have to know also the losses. And we have really to assess the losses, at every point of the city and compare gains and losses. And at the end, we have to try a mitigation strategy which decreases the gains, decreases the sensible heat, and increases the losses, increases the latent heat. So by having, all this information in details, we can design really our mitigation strategy. And the mitigation strategy should be very clear and based on one, let's say, principle. Let's decrease the gains, let's increase the losses. But to do that, you have to know where are the gains, the reason behind the gains, the characteristics of the gains, where are the losses, the reasons behind the losses, and the characteristics of the losses. If you remember, the sensible heat released during, for example, noontime in, let's say, Riyadh was close to 150 watts per square meter. The losses, the latent heat, is just 12, 1/10 of it, even lower, which means that we have an excess of heat gains and we don't have enough heat losses. So now it starts to become, let's say, clear what kind of mitigation strategies we have to use. We have to decrease the heat gains, we have to decrease the sensible heat, we have to increase the losses, we have to increase the, let's say, the evaporative and latent heat losses. How this can be done? How this, let's say, we can decrease the sensible heats? By decreasing the surface temperature. How to decrease the surface temperature? By using materials which do not absorb heat, so they have much lower temperature. By using greenery which really present much lower surface temperature, if really can be used. And how to increase the latent heat losses? By using, let's say, more evaporative, let's say, components at the city scale, which means more greenery or more water, etc. So, based on the whole, let's say, analysis that, of course, I tried really to present you very briefly, there are during the summer period, there are two peaks of air temperature which appeared, let's say, during the June period, with a maximum temperature which exceeds 45 degrees. And we know that the hotspots really appear, let's say, in some parts of the city, the Al Yasmin district, which present very high density. The daily average temperature was between 34 to 39.5 degrees. The maximum temperature was close really to 45.7. 24 hours average of the maximum ambient temperature during the whole summer period was about 40 degrees, and the peak was 43 degrees. Humidity, which define in a way really the potential for latent heat, is low, and this is very good, because once really humidity is low, it allows really for more evaporative losses. If humidity is very high, you can't use really evaporative techniques because the potential for evaporation is very low. And in this case, the use of greenery or of other, water surfaces may not be so, let's say, practical, or may have adverse, let's say, results because may increase really the humidity. But in our case, we had really a low humidity, which is close to 21% during the whole summer period. The urban heat island, it has really some important variabilities with an average of 2-3 degrees, but in some cases and under specific conditions, which really shows a lot of information and give us a lot of information, may go up to, let's say, 9 degrees or close, let's say, to 8 or 9 degrees. This is what is happening during the summer period. During the winter period, we had really two peaks of the air temperature that, let's say, happened during, not June or July, it is on January and, let's say, July. And the temperature, is quite pleasant. It's not so high. Urban heat island remains almost the same like, let's say, during the summer period, very similar characteristic. Humidity is also, let's say, low. I will not insist so much on, let's say, the winter characteristic. We can really go later and discuss this. So we had a very good understanding of the reasons behind the overheating and the characteristics really of the city. But when really all this information is collected, and before really proceeding to the, let's say, design of the mitigation technologies and also the assessment of the mitigation technologies, it is extremely important to, let's say, perform another study, an assessment of the heat risk. So based on the existing data we had about the ambient and surface temperature, humidity, wind speed, etc., we calculated the levels of the thermal discomfort per district. So you see in the graph the levels of thermal discomfort per district. So we found that the eastern district of the city have the most burdensome thermal discomfort conditions relative to those in the western part. The thermal discomfort, let's say, index is higher than 27. That means that most of the people feels really discomfort. But this is something that it is well expected because, you know, in Riyadh, everyone is living under air conditioning. So we have really designed a map of the thermal discomfort and the heat risk assessment for the city of Riyadh, as you can see there. The heat risk assessment should be combined with the climatological assessment that I just, let's say, presented to you. Why have to be combined? Because the ultimate goal is not just to decrease the temperature. The ultimate goal is also to protect, let's say, the population and especially the vulnerable population. So we cannot really design horizontal measures for everyone, for every place we need it. And this brings us to, let's say, the design of the mitigation technologies. So we have a reference, the one I presented you before. We have a model which calculated all the climatic parameters at really high resolution, 250 by 250 meters, with very detailed information in order to compare and validate it, to compare against, let's say, other predictions from other mitigation technologies. And this is the reference scenario. The first scenario that we have really designed had to do with, let's say, the decrease of the sensible heat at the city scale. As I mentioned to you and I showed you, the reference, the reference sensible heat load during noontime is close to 150 watts per square meter. It's not the highest possible. I have seen in other cities, higher urban, let's say, sensible heat released, but it is quite high. How we can really decrease the sensible heat? By decreasing the temperature of the materials. So to decrease the temperature of the materials, we need really to, let's say, decrease the heat gains of the materials and increase the heat losses of the materials. How to decrease the heat gains of the materials? By absorbing less solar radiation. Solar radiation is very strong in Riyadh, and we have to reduce the absorption of solar radiation. But this is not enough. We need really to increase and enhance the losses from the materials. Have the material losses? Of course. Every material, everyone is emitting infrared radiation. And the emission of infrared radiation depends on the so-called emissivity of the materials. The emissivity of the materials have to be high in order to emit as much as possible, let's say, thermal radiation. So the ultimate goal is really to decrease the absorption of solar radiation, and this can be done by increasing the reflectance of the materials, and at the same time, increase as much as possible the losses of the materials, and this can be done by increasing the, let's say, emissivity of the materials. Do we have materials that really have these properties? Yes. Actually, in the market, there are the so-called cool materials. Tomorrow we'll discuss about these materials, which really present these characteristics. These cool materials are available into the market and can be easily, let's say, implemented. These materials are developed during the 90s and they are commercially available everywhere. In India, these materials are really commercially available and also produced by, let's say, the local industry. But this is a very basic scenario trying really to decrease the sensitivity. Is it enough? We don't know. Perhaps we need something more drastic. We need some more intensive. Perhaps we need really to use materials which have better, let's say, reflectance, higher reflectance to solar radiation, and perhaps have really super, let's say, emittance that really increases tremendously the losses. Do we have these materials? Yes. This is the so-called supercool materials. Yesterday, I referred to these materials and I presented a little bit. I will repeat their properties. First, these materials present a reflectance between 95 to 98%, very high reflectance. And because of the very high reflectance, these materials can be used only at the roof of the buildings, cannot be used on pavements because it will create important, let's say, optical problems. But the major, let's say, benefit of these materials is that these materials are not really emitting at the whole, infrared spectrum. The reflective materials that we use in the first scenario, they emit really radiation, infrared radiation, and this is a loss. But this infrared radiation is going to the atmosphere, and the atmosphere, you have to know, is not really transparent to this infrared radiation at every wavelength. So part of this emitted radiation, it is absorbed and then re-emitted or reflected by the atmosphere and returns back to the materials. So although we may have a loss from the materials, in reality, a high part of the emitted radiation returns back to the materials. What's the difference with the supercool materials? You have to know that the atmosphere is really open, transparent to wavelengths between 8 to 13 micrometers. It's the so-called atmospheric window. This is the window that really allows to have, let's say, life, let's say, in our planet. At this wavelength, radiation emitted by the materials, by everything, escape to space, is not absorbed and reflected back. And unfortunately, during the very last years, because of the increase, of the greenhouse gases, the atmospheric window starts really to close, and this is the reason of the overheating. But actually, in non-humid climates, the atmospheric window is quite open. So these supercool materials, apart of the very high reflectance they present, they have another benefit: emit only at the specific wavelengths of the atmospheric window. So they dissipate all the excess heat directly to space. So we send the excess heat of the materials, of the city, if you like, directly to space. And this is the reason that the thermal performance of the supercool materials, it's much more, let's say, superior to the thermal performance of the conventional cool materials. The supercool materials are now available everywhere in the world. There's materials that have different forms, can be a paint, can be a plastic, can be a metal, can be a tissue, can be whatever you want. And it can be easily used at the city scale, but mainly, the white ones at the roof, let's say, of the buildings. The recent years, the last 2 years, we have developed materials, and we will discuss it tomorrow, which really present much lower reflectance and use fluorescence, so can be used also for pavements and also vertical, let's say, vertical surfaces. Then by using these two scenarios, we aim really to decrease the sensible heat. But as I mentioned to you, the goal is also to increase the losses, evaporative losses, increase the latent heat. How this can be done? By, let's say, using greenery. So we design, let's say, a scenario where we increase the green infrastructure of Riyadh up to 30% using non-irrigated low-level vegetation. Why up to 30%? Because in Riyadh, actually, they have space and they built tremendous new, let's say, parks, and also dry because they don't have water. Or they have water, but the water costs really a fortune because this is coming from desalination. So let's try to see if really non-really irrigated can help really the city to increase the landed, let's say, losses. But we're not really very sure about it because there are two parameters that define really the performance of greenery. The size of the greenery and, of course, the potential for, let's say, evapotranspiration. So we created a new scenario where we increase this 30% to 60%. Is it reliable? Perhaps no, but it shows us the, let's say, potential of greenery at the city scale. And then the second parameter is the irrigation. Water, let's say, in these areas is something that is water availability is scarcity, but in reality, you know, the greenery may not operate properly enough of evapotranspiration and not to, let's say, increase latent heat and cooling without irrigation. So we tried two more scenarios. The previous one, but irrigated. 30% with irrigation, 60% with irrigation. And then when really we had the results, we see that it is much better if we combine, let's say, the use of supercool materials together with, let's say, greenery. Together with dry greenery, supercool materials and dry greenery, supercool materials with, let's say, irrigated greenery. These are, let's say, the mitigation scenarios that we have designed. And I explain you why it is important, these mitigation scenarios, to be designed based on a rational and based on the needs and the strategy that has to be, let's say, followed at the city level. I will stop now for 5-10 minutes. If you have any question, we may discuss it now. No questions? Everything is well understood? Yes. I see some questions.
Sir, I think one question is there of Gauri Shinoy.
Can I read?
Yeah, how does the reduction of urban greenery in the existing built environment alter the balance between sensible and latent heat fluxes? And what implication does this have for mitigating urban heat island? Am I audible?
This is the next part of the lecture.
Okay.
Yeah, this is what I will present you later, you know.
Yeah.
In the next hour, I will present you the, let's say, mitigation potential of the different technologies. And you will be surprised a bit.
Okay. Any more question, participants? Actually, sir, your lectures are so clear. I think they have very less questions for you. How to
You have,
enter,
you
how
have to ask questions. You don't have to be shy. You have nothing to lose.
Yeah. Sir. There is one more question Dr. Faiz Ahmed sir has asked how to validate the effectiveness of cool roof or green walls pilot tested something.
How to validate the effectiveness of cool roof. Uh, you know, the thermal performance of cool roofs is something that is very well known, and there are tools that are extremely well validated, about the performance of cool roofs. Uh, it is something really that is validated in thousands of applications all around the world. So, for example, if you are using the well-known, let's say, computer tools or simulation tools like the Energy Plus, etc., they have subroutines for cool roofs, which are very well validated. So this is something that is already done. You don't have every time to validate, the performance of cool roofs. Anyway, cool roof is not something, is not something really special for the building. You just have higher reflectance and a little bit higher, higher emittance. So the let's say well-validated energy, let's say simulation models, they can do it without any problem, and this is done for thousands of cases.
Sir, what would be the most economic strategy for heat mitigation in for a socio-economically deprived settlement?
This is something that we will discuss at the very end, but I will reply you.
Okay.
Economic. I will explain to you. Economic for who? For Saudi Arabia or for India?
For India.
Not the same conditions at all. Economy is not a problem. The cost is not a problem.
No,
No.
what I mean is for the economically challenged. We have lots of squatter settlements in urban areas. So how can we?
The economic challenge, yeah, the economic challenge is really associated with the performance of the mitigation technologies, because you risk really, if you don't have the proper, let's say, simulation stats or the proper, let's say, analysis to implement, let's say, mitigation strategies which do not really give you the proper results. In this case, it's a failure. And although there are myths about, different mitigation technologies, and all around the world, we know just, plant greenery and you will have mitigation. You may have big surprises because greenery may increase the temperature at the city scale. So this is a failure. This is a techno-economical, or an economical failure. But the techno-economical analysis, depends on the availability of the resources and the potential, of the different technologies. In our case here, we never used some, let's say, extremely expensive technologies. The use of these materials is quite cheap, actually. And greenery is something really that does not present so high cost. The operational cost may be higher, especially for, let's say, the irrigation, etc. So personally, when I'm designing, mitigation strategies in different parts of the world, I'm not using very expensive technologies. And I'm trying to avoid in super sophisticated techniques. My, let's say, theory is that make it simple, make it stupid, and make it to work. Don't use, let's say, technologies which really are not familiar, where local people is not familiar with the technologies, and may need a lot of maintenance and difficult operation, because after some time all these technologies will be abandoned. So I think and I believe really that simple technologies, passive technologies, which do not really need a lot of maintenance and do not need a lot of technical knowledge at the city scale, may work better. There are technologies really which present, let's say, a little bit higher potential, but they are complicated technologies, which ask for a lot of expertise and a lot of maintenance. In this case, if you don't have the proper, let's say, the proper the proper knowledge, really at the city level, you risk really to abandon this, and you risk really not to have benefits. We've seen that many times, in different projects implemented in Africa by the World Bank and other international institutions. That they go, for example, in different parts, they include and they install, sophisticated technologies for water treatment or sophisticated technologies for waste management and things like that. There is no the proper knowledge, and after 3, 4, 5 years, all these technologies are abandoned. This is not what has to be there. We have to use, let's say, appropriate technologies which really support and can be supported by the local population.
More like retrofit, sir. Is there anything you would have in mind? More like a retrofit, because it's very difficult to tell this squatter settlement to rebuild something. So with whatever they already have, would there be any strategy or anything that can be used for retrofit of existing low income housing?
Low income. In Saudi Arabia, we don't have what you call low income in India. It's completely different. You have the low income people there who can be Indians, Pakistanis, Filipinos, etc., working there. But the situation is not the same like in India, for example. It's completely different. They have, let's say, houses. They have good quality houses, and they have air conditioning. So the situation is completely different. So the socioeconomic conditions are very different. In Saudi Arabia and in Riyadh, you don't design so much for low-income people. You design for the whole city, and you design also for the vulnerable population. Yes, vulnerable population, yes, especially older population. This can be done. Low-income cities, low-income population, low-income households is something really that has a completely different meaning in this area.
Right. Sir, we have a question from Mr. Vijesh Kumar. What is the appropriate spatial extent for a study conducted at a city scale, considering factors beyond just the administrative boundaries? Also, I wish to know the simulation tools used for this study.
For the simulation tools, I presented that for the, let's say, mesoscale simulation, we use WRF. WRF can simulate, all these climatic conditions. I'm not sure about the first part of the question.
The first part is, what is the appropriate spatial extent for a study conducted at a city scale, considering factors beyond just the administrative boundaries?
I'm not sure that I understand the question.
What can be the size of the study area?
Depends, of the size of the mitigation, let's say, area. In Riyadh, they consider the whole metropolitan area. In some other places, you consider, a part of the city. But the study has to consider, all the neighborhoods which are around, because you cannot really design, for example, a mitigation strategy just simulating the, let's say, conditions in the specific area. For example, many people, they are using EnviMet, and they take, some areas and they calculate the EnviMet. With EnviMet, they know the boundary conditions. You don't know what is happening in the surrounding. You don't know really which is the advection of heat how really the surrounding areas, how really support or really transfer heat there. So the urban environment is not an isolated environment. You cannot really take just one part and simulate this one part. You have to simulate the whole area. As I showed you before, we simulated really an area which covers almost half of the Saudi Arabia, because we wanted really to have into account, to take into account, all the phenomena which transfer really heat from the surrounding to the city or from the city to the surrounding. This is very important. If this is not really taken into account, your results may not be accurate.
How effective are different types of green infrastructure? What is the role of green infrastructure to mitigate urban heat?
This is the next lecture. Okay, let's continue.
Yes.
Okay, thank you. Okay, let's continue. So I have presented you the different mitigation scenarios, and I like to show you the results. You asked me really to show the results and also to, let's say, understand which is the potential, the cooling potential of, let's say, different mitigation technologies. So, first scenario, the use of cool materials, conventional cool materials. Conventional cool materials with, let's say, an albedo for the roofs of 0.75, not so high, for the pavements, 0.4, and an emissivity close to 0.9. Under these conditions, the use of these, let's say, reflective materials may, let's say, contribute to decrease the, let's say, in average, the temperature of the city between 1 to 1.5 degrees. This is something that will go for most of the cities. This is the potential of, let's say, this kind of technologies, 1 to 1.5 degrees. In some cases, and under specific conditions, really we may have a decrease up to 3 degrees, but this is really something very, very, let's say, rare. You have to consider that the use of, let's say, conventional materials of with reflection close to 75-80% may decrease the temperature of the city between 1 to 1.5 degrees. And this, graph shows really the distribution of the average temperature reduction at the city scale really during, let's say, when the conventional materials, reflecting materials are used. And you see that the performance is not everywhere the same. The performance is much higher in dense areas with higher, urban density, and this is normal because you have more materials there, and you have more emissions, more absorption, you have more, let's say, absorption of heat. So you can understand that this technology or this mitigation technology give us a decrease of, let's say, close to 1.2, 1.5 degrees. This is the maximum we can get from these, let's say, materials. And these materials, of course, have an important impact during the daytime, because during the nighttime we don't have solar radiation, we don't have really, let's say, important, let's say, absorption. So the impact of reflecting materials is low. The impact of the reflecting materials is not so low during the night because of the emissivity. And because these materials, they emit really infrared radiation to the sky. So in this case, we have a dissipation of excess heat, and this helps really to decrease the temperature during the night. But the main impact is during the day, and as I repeated before, it's between 1 to 1.5 degrees. On the contrary, we have a very significant really decrease of the surface temperature. And this was the ultimate goal really of this mitigation technology, because we wanted really to decrease the surface temperature and at the same time decrease the, let's say, release of sensible heat. And by using these, let's say, technologies during, let's say, noontime, we succeed to decrease the, let's say, peak surface temperature up to 8 degrees. This is very important because 8 degrees is really a very high reduction of, let's say, heat temperature, which really, surface temperature, which really helps to decrease the surface, let's say, heat. And you can see, for example, the distribution of the sensible heat. In, let's say, we have succeeded.
Can you put full screen mode, please?
It's not full screen?
No, sir.
Okay? I'm sorry.
Yeah. Thank you.
Yeah. Welcome. So, we have seen, for example, that we have, by using this technology, we have succeeded really to decrease the sensible heat, let's say, during the daytime. And also, something which is very important, the wind speed and the temperature zone, let's say, were similar. So when we had really an important decrease of the temperature, we had also an important decrease of the wind speed. And this happens in the southern part of Riyadh. And you have to know that usually when cool roofs are implemented, let's say, the wind speed is decreasing. And this is happening because the planetary boundary layer is reduced. And in this case, we don't have really important, we have a reduction of the wind speed, and there is a risk for accumulation of, let's say, pollution. And there was a very clear, association between the temperature reduction, almost a linear relation with the wind speed. So let's say, the higher the wind speed along, let's say, its latitude, the higher the ambient temperature for, let's say, its grid. So this is the potential of the convective materials. Of the reflecting materials. 1.5 degrees, and especially in the southern part, an important decrease of sensible heat. It helps. It helps a lot. Better? So let's use more sophisticated materials. Super cool materials. Materials which really have a high reflectance, very high reflectance, 0.95, and a very high emissivity, but this emissivity, let's say, on the atmospheric window, 0.95. So in this case, the average reduction of the ambient temperature, was between 1.3 to 3 degrees. And we had really a much higher reduction of, let's say, the ambient temperature because of the, let's say, the supercool materials. But don't forget that the use of the supercool materials now was really restricted to the roofs, while before we had an implementation, both at the city, at the street level pavements and the roofs. Here we have only the roofs, and the average, let's say, decrease of the temperature we achieved with the supercool materials only at the roofs, let's say, scale was 1.3, 1.4 degrees. Between 0.2 to 0.3, 0.4 degrees higher than the previous scenario. But the two scenarios cannot be compared because we don't have the same, let's say, area. And the distribution of the ambient temperature in, let's say, many cases was up to 2, the maximum was close to 2.5 degrees with an average of 1.3, 1.4, 1.5 degrees. So we've seen that really the use of supercool materials really help a lot to, let's say, decrease the temperature, but at the same time decrease, let's say, the surface temperature to 8, 9 degrees. And you may, let's say, ask me, but before you had 8, 9 degrees, because why now you have also the same by using, more sophisticated materials? Because now we don't really, let's say, treat it, the pavements and all the other structure of, let's say, the city. We use only, super cool materials at the roof level. And this also decreased very much at the same time the sensible heat and also the wind speed. I will move a little bit more faster just to finish in half an hour or something like that. And what I like to tell you is that the maximum, let's say, decrease we had with the supercool materials at the roof scale was 2 to 3 degrees. This is very important. On average, it was 1.3, 1.5 degrees, a decrease of the surface temperature close, let's say, to 8, 9 degrees. And now we move to, let's say, the use of greenery, non-irrigated greenery. And by, let's say, covering 30% of the additional space in, let's say, the city of Riyadh. What really we have seen is that by using this kind of technology without really having an important, let's say, irrigation, may, let's say, decrease the temperature of the city between, let's say, 0.4 to 1 degree. But in many cases, we may have an increase of the temperature. And you can see, for example, from the graphs that in some cases, we had an increase of the temperature. Why we have an increase of the temperature when really we have non-irrigated greenery? Because when really temperature is very high, above 35 degrees, which is very common, trees stop to evapotranspirate. And stop to evapotranspirate because really they don't have enough sap and they like to be protected. But because the leaves, the color of the leaves of the trees is quite dark, the temperature of the leaves is perhaps very similar or a bit higher than the temperature of, let's say, the atmospheric temperature or the ambient temperature. As a result, trees contribute to heating. We have seen this many times, especially in, let's say, arid climates in California, etc., in real experiments. But also we know that in many parts of the world, during heat waves, let's say the temperature inside parks is higher than the temperature outside parks. The trees, and also because of the lack of irrigation. So the conclusion was that the use of, let's say, non-irrigated trees could not really help to decrease the temperature of the city, or under very specific conditions, the, let's say, decrease was during the daytime very moderate, during the night was a little bit more higher. And when really we decided to irrigate the water, the trees and the greenery, and to simulate really the impact of the irrigated greenery, it's changed completely. In this case, the decrease really of the temperature we had was up to 1.5 degrees. So in this area, and especially in arid climates, the use of non-irrigated greenery is not helping at all. On the contrary, may increase the temperature of the city. For these, let's say, climatic conditions, it is mandatory to have very strong irrigation. It's implemented, then during the night, the daytime, we may have an important decrease of the temperature up to, and during the night, the decrease of the temperature may be as high as 5 or 6 degrees. So the use of, let's say, additional greenery combined with, let's say, irrigation, it seems to be a very, let's say, efficient methodology for heat mitigation in these climatic conditions. And also, this helps a lot really to decrease the temperature of the city, the surface temperature of the city. Of course, because greenery is not implemented everywhere, the average decrease of the temperature of the city is not so high, like in the case where really we change all the materials. And the same happens also when really we increase the size of parks, but we don't irrigate. The impact, of the size of the parks and the size, of the green area when trees are not irrigated is not really important, especially for this climate. let's say the size of the park is not helping so much, because really the coolness of the parks is not really transported, is transferred more than 350 meters from the boundaries of the park. So by increasing the size, let's say, is not really helping so much, and especially when it is not really irrigated. But once really let's say the temperature, the greenery is increasing, and at the same time it is irrigated, then in this case the temperature reduction may be as high as 4 degrees and 3.5 degrees, as you can see there. So it seems that this is a wonderful technology and a wonderful mitigation technology, really, mitigation, let's say, strategy for these climatic conditions. And the reduction of the temperature during the nighttime may be as high as 9 degrees or 10 degrees. So it seems that this is a very good solution. Of course, it's very difficult really to increase the green infrastructure in the city by 60%, but in reality it is possible because they plan to do that. So we know now the potential, of all these, let's say, mitigation technologies. And it is very important really to combine these mitigation technologies, especially in areas where we have really to increase as much as possible the latent heat, and in areas where we have to decrease the sensible heat really because of the very high surface temperature. So we combine the really solutions in specific parts of the city, trying really to decrease the release of the sensible heat by using supercool materials, and increase as much as possible the use of latent heat by use irrigated real greenery. In this case, we have a decrease of maximum temperature reduction of the city close to 4.5 degrees. This is really an important and the most important, let's say, reduction of the temperature we never had in a city. And also a very important, let's say, reduction in the areas that really are of concern. And you can see, for example, that the nighttime temperature may decrease up to 6-7 degrees. The daytime temperature really may decrease up to 4.5 degrees, depending on the time. So this combination seems to be, seems to be a very efficient, let's say, combination for the specific climatic conditions. And this combination really was the combination that was really adapted to the specific, let's say, conditions. I pass really the results because we don't have enough time, and I like really to show also the energy analysis. So some conclusions. All mitigation measures have a more pronounced cooling effect under hot weather conditions. The higher the background ambient temperature, the higher the cooling potential of the mitigation scenarios. This is very important. In vegetation-related scenarios, the dry soil conditions prevent plants from releasing effective evapotranspiration during the day. And most of the latent heat flux during the day comes from the direct soil evapotranspiration. So we have only evaporation, not soil transpiration. When using plants to alleviate overheating in Riyadh, adequate irrigation must be considered. And the same conclusion has been drawn from many other cities around the world. In high reflective and, let's say, non-irrigated scenarios, let's say the daytime cooling is significant, between 1 to 1.5 degrees. The night decrease of the temperature of the urban heat island was really important, and it can help a lot. At the same time, the use of mitigation scenarios really were where we combine really cool and super cool materials. Seems to be, let's say, a very good technology, especially when we increase the reflectance of the roofs and at the same time the reflectance of the pavements. When really we use cool materials for the pavements and super cool materials for the roofs, we may have a decrease of the temperature up to 2.53 degrees. Vegetation scenarios are very important, but we need irrigation. Without irrigation, there is no really any mitigation potential. On the contrary, we may have, let's say, some negative impacts. So this is let's say, the main conclusions. In these areas, don't use greenery without irrigation. But irrigation in arid areas is not an easy task. They may have water because really they have desalination, but they are using oil for this. It's something that you can't do it in India. We don't have enough water for this. On the contrary, the use of cool and super cool materials may really decrease the peak temperature of cities up to 2.5 degrees, the maximum when they are in combination. In average, you may expect a decrease of the temperature by 1.5 degrees. Given that, we had to assess really the energy impact of the different, let's say, mitigation scenarios we have considered. And how this is done. We simulated really all these measures by, let's say, using advanced heat mitigation scenarios for, let's say, a whole precinct. This is the precinct of Al Masif at the center of Riyadh, and we simulated 3,323 buildings. And this is done in the supercomputer of Berkeley Laboratory in San Francisco, using advanced, let's say, simulation techniques. And we use the so-called city-based, let's say, facility of the Berkeley Laboratory using Energy Plus and Open Studio really as the simulation engine. I don't like really to go through all these details. This paper, this part is published in Nature Cities. If you are interested, I can send you, the paper, and you can see all these details. So, what really we have simulated is, first of all, the number of hours above the threshold. And we use, several thresholds, 27, 30, 35, 36, 37, 38, 40, etc., etc. So we really wanted to understand how many hours we have, above a certain temperature, at the city scale for the different materials and for the different mitigation technologies. And you see, for example, the difference in how really we have decreased the overheating hours by using, let's say, the different mitigation technologies. It's not enough to say that I can decrease in average the temperature by 1.5 degrees. It is very important to, let's say, calculate the, let's say, impact during the whole year and to understand what really helps during the whole year and not just for a specific, let's say, moment. And you can see, for example, that the combination of the greenery, irrigated greenery with supercool materials have a tremendous impact on, let's say, the overheating of the city, decreasing substantially, really, the overheating hours. And the same happens during the day, as you can see here, and also during the nighttime. During the nighttime, we had a much higher, reduction of the overheating hours, especially because of the use of greenery and for irrigated greenery. And believe me, during the nighttime in Riyadh, the decrease of the overheating time is really very important because temperatures are very high. Air conditioning is working continuously, so really this has an impact on thermal comfort, a condition of, let's say, thermal comfort conditions, a quality of life, and also energy consumption. And also we calculated the cooling degree hours, how many hours you need cooling and what is the, let's say, global impact. And also you can see that the impact is very important when the mitigation scenarios are really combined. And then we calculated for each one of, let's say, the buildings, the cooling electricity use, let's say, each one of the buildings. And you see, for example, for all the area, 3,323 buildings, they simulated energy consumption during, let's say, the summer period. So we knew for each one of these buildings, which is really the, let's say, the energy consumption under the reference conditions, and we compare against the real data and under the different mitigation, let's say, conditions. So on average, the combination of, let's say, irrigated greenery together with supercool materials may decrease the energy consumption in Riyadh by, let's say, 16%. On the contrary, by using, let's say, just conventional cool materials, the expected decrease of the energy is close to 5%. Just the supercool materials, 5%. Low-level non-irrigated, 3.9%, and this is because of the night, let's say, because of the temperature. Low-level non-irrigated, 10.6, 60%. And when really we have a combination of, let's say, irrigated and supercool materials, irrigated green and supercool materials, we may decrease the energy consumption by 60%. You may say that 60% is not so high. It is very high. It is very high because this refers, to measures taken, at the city scale, not at the building scale. Because by decreasing, the energy consumption at the city scale by using, technologies which decrease the temperature at the city and not at the building, this is very important. But at the same time, we really wanted to calculate what will happen once really we combine these, let's say, mitigation technologies at the city scale with specific, let's say, measures trying to improve the quality of the buildings. And we consider several retrofitting, let's say, scenarios for the external wall, for better, let's say, ventilation and better, let's say, ventilation and infiltration, better windows, and a number, of measures, which are simple but can be done easily. So in this case, the combination of, let's say, adaptation and mitigation technologies can really offer a decrease of the cooling demand in Riyadh by 36%. 36% at the city scale really of Riyadh is a tremendous number. Is a tremendous number because we are discussing about very high temperatures. So the potential really is extremely high for mitigation of heat, for, let's say, decrease of the temperature, but at the same time, there is a very high potential really for, let's say, very high potential for energy, let's say, conservation and decrease of the energy consumption. I'm sorry. In conclusion, the city of Riyadh is a very warm city, and the temperature of the city is up to 4 degrees higher than that of the surrounding, between 3 to 4 degrees. Overheating creates important problems of discomfort. It is impossible during the summer really to work outside. You need to have air conditioning. By implementing mitigation technologies in Riyadh, we are, let's say, able to decrease the peak temperature up to 4.5 degrees, and the average temperature during the 24 hours close to 2.53 degrees during the summer period. This is a tremendous, really, decrease of the temperature. But to perform that and to achieve that, we have to use really technologies which offer the maximum cooling capacity. And to do that, we need to follow a very specific methodology to design the mitigation technologies. If not, we perform, an empirical approach, a blind approach, the results may be really the worst possible. Unfortunately, this happens in many cities around the world. And because really the lack of knowledge from the decision makers, and because very simplistic suggestions from semi-knowledge persons, all around the world, the decision makers, they select some very simple solutions or simplistic solutions. Let's plant, 5 million trees. This may increase tremendously the water consumption, but if you don't have the water, and in most cases you don't have the water and they don't irrigate, this really contributes to an increase of the temperature. But the worst is not there. The worst is that when trees, they, let's say, they are under, let's say, thermal shock above 35 degrees, they emit BVOCs. BVOCs are biogenic volatile organic compounds. BVOCs are emitted by the trees to communicate between them. It's the language they have. And also, it's really a way to be protected. BVOCs are 3 to 4 times more toxic than the exhaust of the cars. And BVOCs contribute tremendously to the increase of the ozone. So it is of extreme importance when really greenery is implemented in cities to be well irrigated and protect really the greenery. Greenery is a living organism. It's like human beings. We have really to respect them. You don't plant trees and leave them there to do the job. They can't do the job. They need protection. They need really to be supported. And if you don't support greenery, greenery will give you a problem that has to do with temperature and a problem that has to do more with pollution. And the last years, because we have much more higher temperatures, higher frequency of temperatures, in let's say different increase of the pollution inside parks because they don't irrigate the parks. And the water is not enough, evapotranspiration is not enough, and trees really, they are under thermal shock. When trees are under thermal shock, they emit VOCs. And not only this, they have many other, let's say, functions that I don't have the time really to consider and discuss with you. And trees really, under heat stress, they are really the worst possible mitigation technologies. So this is a real and very precise, message to you. Use greenery, fantastic technology, but protect and respect greenery, let's say, when this is implemented. So this is all from me. If you have questions, I will be very happy, really, and I'm sure you will have a lot of questions. I will be very happy, really, to, let's say, discuss with you.
Sir, I think one question is there from Ayushi Dhar. Sir, in order to assess the heat mitigation of vegetation, how do we control for all other interfering factors like building density, water bodies, wind direction, etc.?
This is taken into account by the simulation tools. This is part of the simulation tools. They consider all these parameters. This is the reason that you have to use sophisticated simulation tools. If you don't use sophisticated simulation tools and you don't really consider on this is an empirical study will be wrong completely.
Ayushi, if you want to unmute yourself, want to ask, you can ask. No problem.
Please unmute yourself, Ayushi, if you are asking.
I don't think so. Unable to unmute? Acha, okay. If fine. Anyone else have questions?
Ayushi has the audio issue. Anybody has anything to ask or discuss? Or all your doubts about vegetation and all that is over?
Before you ask me questions that I try to reply, I hope that you have more questions.
Questions are so many actually, or there aren't, sir. It's in extremes. Because here in our context, we are trying to look at how to mitigate urban heat or mitigate heat from entering the house for the socially marginalized people. So and then we would also like to do a practical pilot project. So if you have any advice for us on that, it will be great.
We'll do it in Friday. Friday is, the lecture about low-income population.
Okay. Okay, so that is what. So there is a question. Mr. Srisha Bhatt wants to know how important it is sometimes to compare it with regional climate model in terms of factors like vegetation.
Yeah, there are different models, for vegetation. Um, there are simplistic models, and also there are more, let's say, sophisticated models. Once you perform a study at the city scale, I will you to use, sophisticated models, which take into account, all the parameters. For example, even the sophisticated models until now failed really to simulate the, let's say, reduction of the evapotranspiration above a certain temperature. Until, the very last years, most of the models, or almost all models, have not included really the reduction and cannot predict, the reduction of the evapotranspiration above a temperature. They consider that trees can evapotranspirate, above 35 degrees without problem. And this happened because the actual, let's say, models for evapotranspiration never included this parameter. During the very last years, and because of the experience we have from the very high temperatures, because now we have high temperatures and we can really have experiments with trees, we understood that this is not the case. All trees do not behave the same way. And actually, there is a tremendous database with almost all trees, which really describes the physiological behavior of trees under high temperatures. So this is something that has to be taken into account, and especially in, let's say, very hot and very warm areas like India. This is very important. Otherwise, you risk, and we risk really not to have any result or have, let's say, the cooling benefits of just shading, which is, let's say, 10-15% of the total cooling capacity of trees considering evapotranspiration. So it is very important to consider that, take into account, and consider also the proper, let's say, greenery for the area. If really you don't have irrigation, try to use the greenery with very deep roots, which really can collect water from, let's say, the soil. This is very important. If not, trees will not have enough water, and the transpiration will be almost zero. Trees will dry, and trees, will unfortunately increase the temperature and also create important problems to the local ecology, because drying of trees really affects very much the, let's say, the insects and everything around it. You have to know that one of the reasons that trees emit BVOCs is really to invite, let's say, insects to protect the trees. And there's a hidden life behind this. So it's not only that you increase the temperature or you have more pollution, the whole ecology of the area is really changing. So the conclusion is that mitigation is a science. It's not something empirical. If you don't study and optimize a mitigation strategy, you don't have results. You don't have good results. You may have adverse results. This is very clear. And especially all of those that they are decision makers, please don't use really any strategies if you are not sure about the real scientific.
Okay. So there is one question. What is the effectiveness of combining passive and active cooling technologies such as supercool materials and energy retrofitting to significantly decrease energy consumption in Riyadh's buildings? What does the city currently mostly apply? What about for government support on policy making for using cooling materials?
To combine passive and active cooling systems, what, I'm not sure, active cooling system, you mean air conditioning?
The question is about combining passive and active cooling technologies such as supercool materials and energy retrofitting.
Yeah, but what is the active system? You mean air conditioning or active?
Yeah, so that's a good. So, what do you mean by active cooling techniques? Do you mean advanced passive techniques, or do you mean air conditioning, or using coolers, water coolers? What do you mean, Tarika? Without that, the question, I mean, becomes little difficult to answer. Okay, there's yet another question. Are there any studies which show the relationship of increasing heat intensity with air pollution? And in so, what can be the mitigation strategies?
Yeah. When we have high pollution, the pollution really absorbs and emits back or reflects the infrared radiation emitted by, let's say, the materials. So in this case, the heat released by, let's say, or the heat emitted by, let's say, by the materials is not having the same cooling potential because the atmosphere is opaque, and in this case, the emitted radiation is not escaping to space. So this is the relation we have. But on the other hand, having, let's say, higher pollution, you have a lower solar radiation. And this compensates a little bit, you know, the phenomena. But pollution has adverse effects on everything, you know. So pollution may, let's say, decrease the mitigation potential, especially of the materials, because of the phenomena having to do with the radiative losses, but also decrease the solar radiation. This is a phenomenon, but you know, it's much better to have no pollution for other reasons, not because we decrease the mitigation potential.
Okay, sir. Thank you.
So there is another question. In what context can microclimate simulation tools be used? The context for using microclimate simulation tools.
All these microclimate simulation tools are almost free now. You need to have some experience in order to run these simulation tools, but these simulation tools provide very, let's say, detailed and accurate information about, let's say, the cooling potential of all the, let's say, climatic parameters in the city. So actually we have climatic simulation tools which are very accurate and can provide the proper information, fortunately, because 10, 15 years ago, this was not possible. And when we started designing, you know, simulation, mitigation, let's say, strategies, it was not possible really to evaluate the impact of the mitigation strategies. Now we are able to do it.
Right. Tarika, you raised your hand. Would you want to ask the question directly?
I already asked the question, only just to tell about the active and passive and active cooling technology. That's active means the using mechanical and electrical conditioning to force heating from the system.
Yeah.
Away from
Yeah, absolutely. You know, the performance of the mitigation technologies is much higher when is applied, you know, in free-floating buildings, not in air conditioning. Because the temperature, you know, difference is much higher and the cooling potential is much higher. But once the building is, let's say, air conditioned, also the performance of, let's say, the heat mitigation technology is high. And what I presented you today, it had to do only with air conditioned buildings. In it's impossible not to have air-conditioned buildings.
Okay, thank you.
Any more questions? None, I guess so. Yeah, nothing much.
There is one question, ma'am.
Yeah.
Can you please again elaborate how dry vegetation will lead to environmental problem?
You know, the evapotranspiration by vegetation it happens because mainly of the evaporation by the soil and transpiration by the leaves. To have transpiration by the leaves, which is increased, latent heat, the sap, the flow, the sap flow, the water flow, in the trees, moves to the, let's say, to the leaves, and it is evaporated. Once the sap is low, very low, because of lack of irrigation, and because trees cannot really find the proper water, in this case, you don't have transpiration. And you don't have release of latent heat. And in this case, in most of the trees, the surface temperature of the greenery, of the trees, is higher than the ambient temperature because of really the color of the trees. In this case, you have a release of sensibly heat by the trees. Trees really act like heaters and contribute to increase the temperature in the urban environment. This is something to avoid. This is something really that has to, let's say, be fixed by using proper irrigation.
Well, anybody else? Is there anything you want to ask for the day? No, that's it. Over. Yeah, so, well, I guess if there are no questions, then can we call it a day? No response for this. Right. Thank you, doctor. Thank you. Thank you so much. And we will meet tomorrow for the next.
Bye. Thank you. Thank you so much. Thank you. Bye. Bye.
Thank you, ma'am.
Thank you, sir. Thank you.
Thank you, sir and ma'am.
Yeah.
Very nice session.
Thank you. Thanks, madam. So we will meet tomorrow.
Thank you,
Mr.
ma'am.
Vinny,
Thank you.
Sumati, Pooja, Gauri. Thank you all so much. Thanks, Risha.